Covered material dealing with molecules and atoms, and the next section that we're going to investigate is what happens when these atoms or molecules come into contact with each other or collide with each other. What type of reactions are we going to observe, and what type of reactions could we predict? So the next section is titled Chemical Equations, and a chemical equation is a symbolic representation of a chemical reaction is called a chemical equation. And in these chemical equations, we typically represent the starting materials over on the left-hand side. We give a little arrow and have the final materials over on the right-hand side. So we're mixing two or more things together, and that's going to give us some type of other products. Okay, so the way chemists refer to our starting materials is we define these as reactants, and the end result are going to be the products. So the left-hand side of a reaction is the reactant side. The right-hand side of a reaction is the product side. So when we write these chemical equations, we can say that if we have sodium solid plus oxygen as a gas, the product that we observe is sodium oxide. And the sodium oxide is a solid. And if we remember from our nomenclature, sodium oxide, sodium is a +1 charge, oxygen has a -2 charge, so this has to be Na2O, and it's an ionic compound. So our product is Na2O. When we react the sodium together, sodium is Na, oxygen is going to be represented as O2 because it's what we refer to as a diatomic gas. So in its standard state, oxygen is going to be represented as O2 because it is a diatomic molecule. We'll get back to that in a second. But once we represent this chemical equation, we need to balance it. We need to make sure that the number of atoms on the left-hand side is equal to the number of atoms on the right-hand side. In order to do this, we need to put a 2 in front of the sodium oxide, because there are 2 oxygens over here on our reactant side. That leaves 4 sodiums on the product side. On the reactant side now, we need a 4 in front of the Na. So now this equation right here is balanced. All right? To mention something about balanced chemical equations is that we need to balance chemical reactions because the total number of atoms of each type remains unchanged. And this goes along with the law of conservation of matter. We cannot create or destroy an atom. It can change form, it can change what it's bonded to, but the total number of atoms is going to be the same. Okay? And we can balance these equations by adjusting the coefficients. So we can't change the actual molecule, but we can change how many, or we can represent with a coefficient how many of that particular molecule will be either reacted or produced. One thing I want to come back on before we move to the next section is these diatomic elements. And some elements are more stable to exist as diatomics. Okay? There are 7 of them that you're responsible for knowing: nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. If you look on the periodic table, starting with nitrogen, element number 7, going over to fluorine, coming down to iodine, it makes an upside down L on the periodic table, and in addition, you have hydrogen. So these are the 7 diatomic elements that you're going to need to be responsible for. So if I say nitrogen gas, you need to recognize that that nitrogen gas is N2 and not just N. So here are all our diatomics. They're going to come into play when you're writing out these reactants and products that you observe in the chemical reactions. So we're going to look at 3 main types of reactions in this section: combination reactions, decomposition reactions, and combustion reactions. And in the next video that we put together, we'll go over some tips for balancing these chemical reactions. We've now discussed what a chemical reaction is, and one of the most important aspects in determining a lot of chemical properties and interpreting observations is balancing chemical reactions. So I'm going to put together a couple tips in this video to help you balance these chemical reactions and to kind of come up with a scheme in order to do so. So tip number 1 would be that if a reaction has unbalanced atoms other than hydrogen and oxygen, first balance them, then balance the hydrogen and oxygen. So for example, if we had C3H8 as a gas plus O2 as a gas, giving CO2 as a gas plus water, also in the gaseous state, we want to first balance all the other species, then come back and do the hydrogen and oxygen. So in this case, we have 3 carbons on the left and only 1 over on the right. So we're going to put a 3 in front of the CO2. That balances out the carbons. Now we want to figure out how to balance the water over here on the right hand side. So if we have 8 hydrogens on the left and only 2 on the right, we need to put a 4 in front of the water. If we now look over on the right hand side, there's 6 plus 4 or 10 total oxygen atoms. So we need to put a 5 in front of the O2, and this is going to balance out that particular reaction. Okay? The second step, and you can kind of, this kind of goes in order, we're kind of going to be all over the place here a little bit. So the second tip is we want to balance polyatomic ions, and remember they're the ones you needed to memorize from the tables in the text, as single entities if they appear on both sides of the equation. So if we have PO4, we want to make sure that you consider that a single entity, because the phosphorus and the oxygen are not coming apart. They're going to stay together as that ion. So, for example, if we have CaCl2 plus H3PO4 giving us Ca3PO4 twice plus HCl, we want to consider each of these polyatomic ions as a single entity. So if we look here, one of the first things we could do is balance the calciums. So we have 3 calciums on the right, only 1 on the left. So we're going to put a 3 in front of that CaCl2. That will give us 6 chlorines on the left. We only have 1 on the right, so we're going to put a 6 in front of that HCl. This gives us 6 hydrogens on the right, 3 hydrogens on the left. We can put a 2 in front of that PO4, or H3PO4, which then will allow us to balance that chemical equation. And note that we don't consider the phosphorus and the oxygen separately in the phosphate group, because that is a polyatomic ion that's going to be very stable, and it's going to, stay together and not break apart. Okay? The third tip is going to be to begin with unbalanced atoms having a charge greater than 1. So for example, if we have K2S plus AlCl3 giving Al2S3 plus KCl, the first thing we're going to look into balancing is the one with the largest charge, which in this case would be aluminum. On the right hand side we have 2 aluminums, on the left we only have 1. So we want to put a 2 in front of the AlCl3. The second thing we can look at is the sulfur. Here we have K2S, and over on the right we have Al2S3. So you have 3 sulfurs on the right, 1 on the left, so we're going to put a 3 in front of the K2S. This gives us 3 sulfurs, 2 aluminums, so everything is balanced with that first complex on the right. The KCl, we now have 3 times 2 or 6 potassiums and 2 times 3 or 6 chlorines. So we need to put a 6 in front of the KCl. So that will allow us to kind of double check to make sure that we have the right number of atoms on each side of this particular equation. The next tip that I'm going to give is that if there are an even number of atoms on one side and an odd number of atoms on the other, begin by multiplying the odds by 2. So for example, if we have nitrogen, which is a diatomic gas, plus hydrogen, which is also a diatomic gas, giving NH3, in this case we have an odd number over on the right hand side. So with the number of hydrogens. So let's multiply the odd number by 2. That gives 2 nitrogens and now 6 hydrogens. We already have 2 nitrogens on the left. Now we're going to put a 3 in front of that hydrogen also to give 6, which 2 times 3, we have 6 hydrogens also on the product side. So if you're kind of stuck and you're not knowing what to do and you have an odd number, just multiply it by 2 and see how that works out, and it'll help balance things out. Last step, always check your work. If you can count properly, you're going to know if you're correct, because the number of atoms on the left-hand side has to equal the number of atoms over on the right-hand side. This section, we're going to analyze patterns of chemical reactivity. And there's 3 types of reactions that we're going to analyze. First, combination reactions. Second, decomposition. And third, combustion. So, in a combination reaction, we have 2 substances forming one product. And an example of one of these reactions would be carbon monoxide, which is CO gas, plus oxygen as a gas. Remember, oxygen's diatomic, giving CO2 as a gas. We have 2 of these substances forming one product. So, as always, we need to make sure that these are balanced. If you notice, we have 3 oxygens on the left and 2 over on the right. So we're going to need to put a 2 in front of the CO2. That'll give us 4 oxygens and 2 carbons on the right. We need 2 carbons now over on the left, so we'll need to put a 2 in front of the CO, which now will give us 2 carbons and 4 oxygens on each side of the equation. Another example of a combination reaction would be SO2 gas plus water in the gaseous form, giving H2SO3, also in the gaseous form. Now we have to make sure this equation's balanced, and if we look, there's 1 sulfur on the left, 1 on the right, 3 oxygens on the left, 3 on the right, 2 hydrogens on the left, and 2 on the right. So this equation, as written with coefficients of 1 in each case, is totally balanced. So there's 2 examples of combination reaction. The next example would be decomposition. In a decomposition reaction, it's actually the opposite of a combination reaction. Here we have 1 reactant yields 2 products. In this case, an example would be something like calcium carbonate, which is CaCO3, as a solid. If we heat this up, it becomes calcium oxide as a solid plus CO2 as a gas. We need to double check to make sure this is balanced. We have 1 calcium on the left and 1 on the right, 1 carbon on the left and 1 on the right, 3 oxygens on the left, and 1 plus 2 or 3 oxygens on the right-hand side. So that is balanced. And typically with these decomposition reactions, you need to put some type of energy or heat them or do something to break down what that reactant is. Some of them happen spontaneously, but in most cases we need to apply some type of energy to push this reaction forward. Another example of this is if we have water in its liquid form and we perform electrolysis, we can get the products hydrogen gas and oxygen gas. In terms of balancing this particular reaction, we have 1 oxygen on the left and 2 on the right. So we need to put a 2 in front of the water. That gives us 2 oxygens, but now we have 4 hydrogens on the left, and we need 4 on the right, so we need to put a 2 in front of the H2 gas. So there's 2 examples of decomposition reactions. The last main form of reactions that we're going to look at is something called a combustion reaction. And in a combustion reaction, typically we have a hydrocarbon plus oxygen gas. It's going to be heated to give us CO2 as a gas plus water. So oxygen always shows up as a reactant, and the products in a combustion reaction are always going to be CO2 plus H2O. This defines and characterizes what a combustion reaction is. So let's talk about how we might balance one of these combustion reactions. So we'll give an example of C7H16 as a gas plus oxygen as a gas. If we heat these up, this is going to give carbon dioxide plus water. And again, remember, combustion reaction, we're always going to see oxygen as a reactant and CO2 and H2O as products. In these combustion reactions, I think taking the following steps would be important. 1, you want to first balance the carbon. Second, you want to balance the hydrogen. And third, balance the oxygen. This is going to be very, very helpful, and if you follow this order, you're going to make it a lot easier on yourself. So first we have C7H16. Okay, so there's 7 carbons on the left and there's only 1 over there on the right. So we need to put a 7 in front of the CO2. Now we have the carbons balanced. Next comes the hydrogens. In terms of the hydrogens, we have 16 hydrogens on the left and only 2 on the right. So we need to put an 8 in front of the water on the right-hand side. Now we need to count up our oxygens. We have 7 times 2, or 14, plus 8 times 1, or 8. And 14 and 8 is going to be 22. So in order to get 22 oxygens on the left, we need to put an 11 in front of the oxygen gas. So and this is going to give you kind of a way to look at these combustion reactions and figure out the best way to balance them, because remember, balancing chemical equations is very important for everything else that we're going to study involving calculations around this topic. In a previous section, we discussed Avogadro's number and the mole, but I want to reiterate here that 1 mole is going to equal 6.022 times 10 to the 23rd of something. And using this conversion, we can now start looking at different terms and putting some definitions together. And one of those that's going to be the most important for us is something called molar mass. And molar mass can be described in the following way. The atomic weight of an element in atomic mass units is numerically equal to the mass in grams of 1 mole of that element. So what we can say is this. If I have one atom of chlorine, we know its atomic weight, or the mass of one of those atoms, is 35.5 AMU. What this definition tells us is if we have 1 mole of chlorine, it's going to be numerically equal to this mass in grams. So 1 mole of chlorine is going to be 35.5 grams. We can say the same thing for a gold atom. The atomic weight of gold is 197 atomic mass units. This tells us that 1 mole of gold is going to be equal to 197 grams. These same rules will apply to molecules. If you have a molecular weight of a particular molecule, you can then determine how many grams 1 mole of that molecule will weigh. So let's do an example problem. And the example problem we are going to do is it will ask us to determine the molar mass of glucose. And glucose is C6H12O6. So we need to determine this molar mass. So remember that when we look at a formula weight, the units are going to be in atomic mass units, and a molar mass is going to be units of grams per mole. These two quantities right here are equivalent numerically. So now let's look and let's determine what the formula weight, or how much 1 molecule of glucose will weigh. In 1 molecule of glucose, we have 6 carbon atoms, we have 12 hydrogen atoms, and we have 6 oxygen atoms. Now we can look at the periodic table to see how much 1 atom of carbon weighs. If we look, there's going to be 6 times 12.0 AMU. For the hydrogen, we have 12 of those times 1.0 AMU. If we now look at the oxygens, we have 6 oxygen atoms times 16.0 AMU. And the atomic mass units can all be calculated directly off of the periodic table. If we multiply 6 times 12, we get 72.0 AMU. 12 times 1 is 12.0 AMU. And 6 times 16 is 96.0 atomic mass units. Adding all of these together, we get 180.0 AMU. So this will be the formula weight for 1 molecule of glucose. We know from this statement that 1 mole, or 6.022 times 10 to the 23rd molecules, has a mass of 180.0 grams. And this 180.0 is going to be our molar mass. So that is the molar mass of glucose. Our next example problem asks us how many oxygen atoms are present in 53 grams of Na2CO3. So we are now going from, we're going to have to go from grams to moles, then from moles to atoms. So we know that 1 mole of Na2CO3 is equal to 6.022 times 10 to the 23rd Na2CO3 molecules. And we can use the periodic table to determine how many grams are going to be present per mole. So if we look at the periodic table, sodium has a molar mass of 23, carbon 12, oxygen 16. So 23 times 2 plus 12 plus 3 times 16 is going to equal 106 grams. So 1 mole of Na2CO3 is equal to 106 grams. We are initially starting out with 53 grams of Na2CO3. So first we need to convert these grams over to moles. We know that 1 mole of Na2CO3 is equal to 106 grams. So we'll put the 106 grams of sodium carbonate down here in the denominator. Then in the numerator, we have 1 mole of Na2CO3. We also know that for every 1 mole of Na2CO3, there are 3 moles of oxygen, because there's 3 oxygens in this particular formula. For every 1 mole of oxygen, there are 6.022 times 10 to the 23rd oxygen atoms. So if we're trying to determine the number of oxygen atoms, we first need to go from grams of sodium carbonate to moles of sodium carbonate, then moles of sodium carbonate to moles of oxygen, and moles of oxygen to atoms of oxygen. When we go through and perform this calculation, we get 9.0 times 10 to the 23rd oxygen atoms. And we need to now check for our significant figures. We initially start with 2 significant figures. When we're making conversion factors with one in terms of grams and moles and how many moles you have in different coefficients here, those are exact numbers. So they're going to have an infinite amount of significant figures. So what's limiting us in this calculation is the 2 significant figures from the number 53 in terms of grams of the sodium carbonate. So our final answer has to have 2 significant figures, and we have it here listed correctly. So 53 grams of sodium carbonate are going to have 9.0 times 10 to the 23rd oxygen. So now that we've established the rules for calculating formula weights and moles and Avogadro's number and everything like that, we can now perform many calculations around these concepts. So the first example problem we're going to look at is how many moles of N2O are present in 100.0 grams of N2O. We now know that 1 mole of N2O is going to equal 2 times 14.00 grams plus 1 times 16.00 grams, or 44.00 grams of N2O. This is how much 6.022 times 10 to the 23rd N2O molecules is going to weigh. So if we have 100.0 grams of N2O, we can now set up a conversion factor problem and use dimensional analysis. Our given unit is grams of N2O, and the desired unit we want is moles of N2O. We know that 44.00 grams of N2O is equal to 1 mole of N2O. So using the numerator-denominator form, we can say that 100.0 grams of N2O times 1 mole of N2O over 44.00 grams of N2O we cancel out the grams. We're left with moles of N2O, and this gives us 2.273 moles of N2O. Keeping in mind the rules for significant figures, we have 4 significant figures. We do the multiplication. Everything in here has 4 significant figures as well. So 100 grams of N2O is going to be 2.273 moles. So here we're asked, what is the mass percent of each element in copper 2 nitrate, which is CuNO3 twice? So we've already talked about molecular weights and how to calculate them, and we're going to need the molecular weight to solve this problem. So we're going to assume that we have 1 mole of CuNO3 twice. So if we have 1 mole, we needed to figure out how many grams of each species, or how many grams this mole is going to weigh. So in terms of copper, there's 1 copper atom in this complex, and we know that that's going to have a molar mass of 63.5 grams. So we have 63.5 grams coming from the copper. In the nitrogen, we have NO3 twice. So there's going to be 2 nitrogens times 14.0 grams. That's going to give us 28.0 grams. The oxygens, there's 3 times 2, or 6 total, times 16.0 grams, is going to give us a mass of 96.0 grams. So for every 1 mole of copper 2 nitrate, we are going to have 187.5 grams. So now we can use the mass percent, and our formula for mass percent is going to equal the mass of X divided by the total mass. Then we need to take this decimal and multiply by 100%. So our mass percent of copper is going to equal 63.5 grams of copper divided by our total mass, which is 187.5 grams, times 100%. This gives us 33.9% copper. Our mass percent of nitrogen is going to equal 28.0 grams of nitrogen divided by the total mass, which is again 187.5. We multiply by 100%, and that gives us 14.9% nitrogen. The mass percent of oxygen is going to equal 96.0 grams divided by 187.5 times 100%. This is going to give us 51.2% oxygen. And as a double check, we can add all these together and they should add up to 100%. And then in this case, they do. So to kind of recap, if you're ever asked to determine the mass percent of each element in a particular complex, assume you have 1 mole of the substance, calculate its molar mass. Then to get the mass percent, you take mass of the component X divided by the total mass. So we take the mass of the copper, the nitrogen, and the oxygen, respectively, in each case, divide them by the total mass, or the molar mass, of the entire compound, multiply each of those by 100%, and that will give you the percents that are listed here on the right. Our next section deals with empirical formulas. And an empirical formula is the smallest whole number ratio of atoms in a compound. And there's a couple steps that we're going to take to determine an empirical formula. The first step will be to express the composition in grams. If the percents are given, assume a 100-gram sample. The second step is determine the number of moles of each element. Step number 3 would be to divide by the smallest amount of moles. Step 4, multiply by a factor to get whole numbers. And as a rule of thumb, if you're within 0.1 of a whole number, the factor is 1. The last step will be write the formula, or the empirical formula in this case. Now, these steps are going to make much more sense when we do an example, and that's exactly what we're going to do. The example problem we're going to perform based on empirical formulas is the following. A compound was analyzed in the lab and found to contain 69.6% manganese and 30.4% oxygen. What is the empirical formula of the compound? So, step number 1, we are going to assume a 100-gram sample. If this is the case, we will have 69.6 grams of manganese and 30.4 grams of oxygen. So the next step is to convert each of these quantities in grams over to moles, because when we list a chemical formula, it lists the ratio of moles present. So here we have 69.6 grams of manganese times, if we look on the periodic table, there are 54.94 grams of manganese in 1 mole of manganese. This gives us 1.27 moles of manganese. Next, we take the 30.4 grams of oxygen times 1 mole of oxygen in 16.00 grams of oxygen. This gives us 1.90 moles of oxygen. So now we've determined the number of moles for each element, and we now need to divide by the smallest number of moles. So that's going to be the 1.27. So we're going to divide both of these numbers by 1.27. That gives 1.00 moles of manganese, and that's going to give 1.496 in terms of the moles of oxygen. So the next step will be to multiply by a factor to get whole numbers. If we want whole numbers of each of these, and when you do these particular problems, you're probably going to observe decimals like 0.5, 0.25, 0.333, 0.1666667, numbers like that. So in this case, we have 1.5, which would be 3 halves. So what we need to do is we need to multiply this 1.49 times 2. Okay? When we do that, that's going to give us a whole number factor, or that's going to equal 2.992, which we can just assume is going to be 3. For the manganese, we have to do the same thing. And when we do that, we're going to get 2.00. So now we have each of these, the ratio, whole number ratio, or the smallest whole number ratio, and we can write our empirical formula. So the empirical formula, based on this data that we're given, is going to be Mn2O3. So again, to reiterate, we first express the composition in grams. Okay, we're not given grams here, we're given percentages, so we're going to assume a 100-gram sample. That gives 69.6 grams of manganese and 30.4 grams of oxygen. We now need to determine the number of moles of each of those elements, so we convert grams to moles. That gives us our moles for both the manganese and the oxygen. Then we divide by the smallest number out of those two, in this case the 1.27. That gives us 1 mole of manganese and 1.496 moles of oxygen. We now need to multiply by a factor to get whole numbers. Our whole numbers are going to come out to 2 to 3, and that's going to be the smallest whole number ratio or empirical formula for manganese oxide. So in this case, our empirical formula is going to be Mn2O3. And if you follow this same setup, you'll be really solid for all your empirical formula calculations. If the empirical formula is known for a particular compound, we can calculate its molecular formula, provided we have either the molecular weight or the molar mass for the compound. So, for example, if we have an empirical formula that is CH, it's the smallest whole number ratio of carbon to hydrogen. But that also means we could have something like C2H2 or C6H6. Each of these are molecular formulas. So, to determine the molecular formula from experimental data, the molecular weight must be known. A multiplying factor is then used. So our factor is going to be equal to the molecular weight divided by the empirical formula weight. And in the next video, we will do an example of how to go from experimental data, calculate the empirical formula, and then determine the molecular formula. The following example is going to show us how to calculate a molecular formula. So first, we're going to have to determine an empirical formula from the information given, then use our factor to determine what the molecular formula is. In this problem, experimentally, it was determined that a compound with a molecular weight equal to 181.4 grams was 39.72% carbon, 1.67% hydrogen, and 58.61% chlorine. What is its molecular formula? So we're going to use the same rules and determine an empirical formula, and we're going to assume a 100-gram sample. If this is the case, that's going to give us 39.72 grams of carbon, 1.67 grams of hydrogen, and 58.61 grams of chlorine. Now we need to convert each of these over to moles. For every 1 mole of carbon, there's 12.0 grams. So this is going to give us 3.307 moles of carbon. We have 1.67 grams of hydrogen. We need to convert that over to moles. For every 1 mole of hydrogen, we have 1.01 grams. This gives us 1.65 moles of hydrogen. Lastly, we need to convert the 58.61 grams of chlorine over to moles. For every 1 mole of chlorine, there's 35.5 grams. This gives us 1.653 moles of chlorine. Now that we have each of the moles of these components, we need to divide by the smallest number. That will be 1.65. So we need to divide all 3 of these by 1.65. This is going to give us 2 moles of carbon, 1 mole of hydrogen, and 1 mole of chlorine. That gives us an empirical formula from this data of C2HCl. So now the next step is to determine the empirical formula weight. Because we know the molecular weight is 181.4. So if we have C2HCl, we have 2 times 12.0 grams plus 1 times 1.01 grams plus 1 times 35.5 grams. This is going to be the empirical formula weight of this particular complex. So that is going to give us 60.5 grams for our empirical formula weight. The next step is to figure out what kind of factor we have. So remember from the previous video, our factor is going to equal the molecular weight divided by the empirical formula weight. The molecular weight is given in the problem as 181.4 grams. The empirical formula weight is 60.5 grams. If we do the calculation, that gives us a factor of 3. So we're going to have to take 3 times the C2HCl, which is going to give C6H3Cl3, and this is our molecular formula. Now let's kind of recap what we've done here. We were given some experimental data. From that experimental data, we can calculate an empirical formula. If the molecular weight is greater than the empirical weight, it's going to be greater than that by a particular factor. So once we determine the empirical formula, we can use the periodic table to determine the empirical formula weight. In this case, our empirical formula was C2HCl, giving an empirical formula weight of 60.5 grams. Then we take the molecular weight divided by the empirical formula weight, which gives us a factor. So we multiply the 3 times the subscripts of the C2HCl, giving us C6H3Cl3. And this is the method that you will use if you're given some data and asked to calculate a molecular formula. In the stoichiometry section, we can investigate the quantitative significance of a balanced chemical reaction. And what this is going to allow us to do is determine the number of grams that need to react, and it can also give us the number of grams of a product that is produced in a chemical reaction. So the example that we're going to look at is CO, carbon monoxide, plus hydrogen gas, giving CH3OH. So first, we need to balance this particular reaction. And in order to do so, we need a coefficient of 2 in front of the hydrogen. So we have CO plus 2H2 giving CH3OH. And notice that for every 1 mole of CO and 2 moles of H2, we get 1 mole of our product, which is CH3OH. And what we can say about this is that stoichiometric factors relate the molar amounts of any two substances in a chemical reaction. So the balanced chemical equation gives us the ratio of all the moles of every component that's involved. So here we have a 1 to 2 to 1 mole ratio of everything, of all the reactants and the products in this particular equation. So from this we can answer various examples, like the following. So in this example, we're going to ask how many moles of H2 is needed to produce 5.4 moles of CH3OH. So initially, we're going to start with our 5.4 moles of CH3OH. That's our given unit. We're going to use dimensional analysis to figure out how many moles of hydrogen are needed to produce this. So if we have 5.4 moles of CH3OH, we now need to go back up and look at the coefficients in the balanced chemical equation. And like we said, stoichiometric factors relate the molar amounts of any two substances in a chemical reaction. So for every 1 mole of CH3OH that are produced, we are going to need to consume 2 moles of H2. So the moles of CH3OH cancel, and this is going to give us 10.8 moles of H2. And this conversion right here comes from the balanced chemical reaction. And this is why we spent a decent amount of time balancing chemical reactions, because the balanced chemical reaction is going to allow us to determine which or how much of a particular product is produced and how much of that reactant we need to produce the amount of the product. So if we kind of provide a template for all the calculations we can do with stoichiometry, we know that in general, in a reaction, we can take moles of component A and interconvert to moles of component of species B. These can either be reactants or products. And the balanced chemical reaction is going to allow us to do this, just like we did in that previous example. We can also convert moles of species B to grams of B. And we can do this by using the molecular weight. We can convert from grams to moles and from moles to grams. Now, we can also go over here to species A and convert moles of A to grams of A. And we can convert grams of A to moles of A. And again, we use the molecular weight in order to do this. Unfortunately, there's no direct step to convert grams of A to grams of B or vice versa. So if we're given grams of component A, and we're trying to get grams of B, we can't do it in one step. We first need to use dimensional analysis to convert from grams of A to moles of A by using the molecular weight, convert moles of A to moles of B from the balanced chemical equation, and moles of B to grams of B using the molecular weight. So we can do a quick example using the following balanced chemical equation. We have 4NH3 plus 5O2 giving 4NO plus 6H2O. What we need to determine here is how many grams of H2O would be formed from the complete reaction of 5.0 grams of NH3. So here we're going to take grams of NH3, convert to moles of NH3, moles of NH3 to moles of H2O, then moles of H2O to grams of H2O. So we'll start with our given quantity, which is 5.0 grams of NH3. There are 17.0 grams of NH3 in 1 mole of NH3. And we can do that by using molecular weights from the periodic table. Now we need to convert moles of NH3 to moles of H2O. We use the coefficients in the balanced chemical equation. There are 4 moles of NH3 for every 6 moles of H2O. So 4 moles of NH3 go in the denominator, and 6 moles of H2O will go in the numerator. The last step is to convert the moles of water to grams of water. So for every 1 mole of H2O, we can add up everything from the periodic table to get 18.0 grams of H2O. This will give us 7.9 grams of H2O. So when we look at what we're doing, this is our given quantity, which is 5.0 grams of ammonia. We then can use the molecular weight of A from our chart up here to convert from grams of ammonia to moles of ammonia. Then, from the balanced chemical reaction, we can convert from moles of ammonia to moles of water. Finally, we use the molecular weight of B to convert moles of water to grams of water. This gives us how many grams of water are produced when 5.0 grams of ammonia reacts. Here I have listed the same reaction that we analyzed in the previous video. And what I want to really emphasize here is what is actually happening at the atomic level when a chemical reaction occurs. So let's just say we have the reactants here in some sort of container. And in this container, I'm going to represent oxygens with clear open circles. So we have 5 O2 molecules over here. So when we have each of these molecules, that's going to give us 10 oxygen atoms. In addition, we have 4 ammonias. So we're going to write nitrogen, kind of shade them in like this, and there's going to be 3 hydrogens around each one of these nitrogens. So our four ammonia molecules are going to look like this. So with 4 ammonias, we have 12 hydrogen atoms, and we have 4 nitrogen atoms. So 10 oxygens, 12 hydrogens, 4 nitrogens. Over here on the product side, we can also pictorially show what happens in going from reactants to products. In this case, we're going to form 4 NO molecules. So an NO is going to have a slightly shaded atom and an open circle. So we're going to get 4 of those, and then we're going to have 6 waters. The waters are the oxygen with 2 hydrogens on each side. So this is an atomic representation of what's happening on the reactants and the product side. And let's count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oxygen atoms. We'll count in the larger, slightly filled in spheres, which will be 4 nitrogen atoms. And then counting up the small filled in dots, which are the hydrogen atoms, there's going to be 12 of them. So on each side of this reactants and products, we have to say that the number of atoms must be conserved. And this is the exact ratio in which these molecules will react. We have 4 ammonias and 5 oxygens producing 4 NOs and 6 waters. So this is the atomic picture. That's what's going to happen when the reactants are mixed together, forming these products. What we're going to talk about next is what happens when we have an excess amount of either one of these reactants, and how will that influence how much product we form. As we alluded to in the previous video, one of the reactants in a particular reaction will run out first. And how does that influence the products? So the next topic we're going to consider is something called limiting reactants. So we can say that the reaction for commercial hydrogen cyanide is 2CH4 plus 3O2 plus 2NH3, giving 2HCN plus 6H2O. If 1.0 kilograms of each reactant is available, how much HCN could be produced? So the first thing that we're going to have to do is determine what's called the limiting reactant. And that is what's going to run out first. So we have 1 kilogram of CH4, we have 1 kilogram of O2, and we have 1 kilogram of NH3. When we react those together, we're trying to figure out how much HCN is produced. So why don't we take 1 kilogram or 1,000 grams and use stoichiometry and dimensional analysis to figure out how many moles of HCN could be produced from 1,000 grams of each reactant. So if we have 1,000 grams of CH4, From the periodic table, we know that 1 mole of CH4 is going to be equal to 16.0 grams of CH4. Then from the balanced chemical equation, for every 2 moles of CH4 that reacts, we have 2 moles of HCN that are produced. This is going to give us a total of 62.5 moles of HCN. Now we do the same calculation for 1,000 grams of O2. From the periodic table, 1 mole of O2 is 32.0 grams. From the balanced chemical equation, we need 3 moles of O2 to produce 2 moles of HCN. This is going to give us a total of 20.8 moles of HCN. Lastly, we take 1,000 grams of NH3, and for every 1 mole of NH3, that's going to equal 17.0 grams. From the balanced chemical equation, for every 2 moles of NH3, we have 2 moles of HCN. This gives us a total of 58.8 moles of HCN. So now we can look at these and see the amount that was produced if 1,000 grams of each of our reactants reacted completely. So the smallest number of moles produced is going to be produced by consuming all of the O2, or the oxygen gas, because 20.8 moles of HCN is the smallest amount here listed. So the thing that's going to determine, or the species that's going to determine how much HCN is produced, is going to be the oxygen. Okay, so we call that, we can say therefore O2 is the limiting reactant, because that's going to dictate how much HCN can be produced. So we've already calculated the moles of HCN produced from 1,000 grams of oxygen. So now we just need to convert this over to grams, because 20.8 moles of HCN will be produced. From the periodic table, 1 mole of HCN is going to be 27.0 grams. When we do that conversion, we get 5.6 times 10 to the second grams of HCN. And this is the amount of HCN that's going to be produced when we react 1,000 grams of CH4, 1,000 grams of O2, and 1,000 grams of NH3. To kind of recap, you calculate how many moles of HCN would be produced if all 3 of these reactants totally reacted, then investigate which one would be the smallest amount of HCN in terms of moles. In this case, the oxygen produces the smallest amount. We call that the limiting reactant. And then from there, once we determine the amount of moles of HCN produced from the limiting reactant, we can use stoichiometry to calculate the mass of HCN that will be produced. In addition to calculating limiting reactants and how much of a product is produced, we can determine how much of one of the other 2 reactants is left unreacted. So in this example, we're going to ask how much NH3 is left unreacted if 1.0 kilograms of NH3 reacts with 1.0 kilogram of oxygen and 1.0 kilogram of methane in the following reaction. So same reaction from the previous problem. We know that from the previous problem, the limiting reactant is going to be O2, and that 20.8 moles of HCN is going to be produced. So the first step that we want to ask ourselves is we want to know that how much NH3 is required to produce 20.8 moles of HCN. So we're going to start then with the 20.8 moles of HCN. And we know from our balanced chemical equation that for every 2 moles of HCN, we have 2 moles of NH3. We now need to convert the moles of NH3 over to grams of NH3. So 1 mole of NH3 is 17.0 grams of NH3. When we do our conversion factor and do the math, we get 354 grams of NH3. Now, when we start calculating these things, we want to know, and I'm going to try to emphasize, how would we express this number in a sentence? This is 354 grams of NH3, and when we express this, we can say that 354 grams of NH3 is required to produce 20.8 moles of HCN. So we know that oxygen limits this particular reaction. It's the limiting reactant, and we're going to have 20.8 moles of HCN produced. We need to figure out how much ammonia that's going to be required to produce that amount. We calculated that to be 354 grams. So in terms of the amount of NH3 left unreacted, we're starting with 1.00 kilogram, or 1,000 grams of NH3. We're going to subtract 354 grams, which is the amount that was required to produce the 20.8 moles, and that's going to give us 646 grams of NH3 that is unreacted after 1,000 grams of O2 is consumed. So we still have 646 grams of the ammonia left after all of the oxygen is used up. So we will call this an excess reactant. So in this particular problem, oxygen is the limiting reactant, and the excess reactants are NH3 and CH4. And when we can do the exact same calculation for CH4 to see how many grams of that are unreacted in this particular problem. The last topic we're going to tackle in this section of the textbook is called percent yield. And all calculations we've performed to this point have been assuming perfect ideal conditions. These ideal values are called the theoretical yield. What we actually obtain in the lab is known as the actual yield. And it's very important to know, especially in industry, when money is on the line, how close to the theoretical yield a reaction is going to come. And we refer to that as the percent yield. And the percent yield is going to be the actual yield divided by the theoretical yield times 100%. So let's look back again to our previous reaction. So suppose we carried out the previous reaction and obtained 410 grams of HCN. And remember, the theoretical yield was equal to 560 grams of HCN. So what is the percent yield of HCN? And again, our percent yield, we're going to use the formula listed right in here inside this box, is going to be equal to the actual yield, which was 410 grams of HCN, divided by the theoretical yield, which is 560 grams of HCN, times 100%. And when we multiply this out to two significant figures, we're going to get 73% for our percent yield. So typically when we calculate a percent yield, we need to determine the theoretical yield from the data that was given. They will give you the value of what was obtained in the laboratory, and then you take that actual yield determined in the lab, divided by the theoretical yield that you calculated, multiply by 100%, and you'll get the percent yield. The following example problem that we're going to perform ties together a lot of the concepts that we've been looking at from this section of the textbook. And it is as follows. Freon 12 has been used as a refrigerant and an aerosol propellant. It is prepared by the following reaction. 3CCl4 plus 2SbF3 giving 3CCl2F2 plus 2SbCl3. When 115 grams of CCl4 and 115 grams of SbF3 react, 80.0 grams of CCl2F2, or Freon 12, was recovered. Calculate A, the limiting reagent, B, the theoretical yield, and C, the percent yield. So, in order to calculate our limiting reagent, or limiting reactant, we have to first start with the mass given for each of the reactants. So the first calculation is we're going to take the 115 grams of CCl4 and convert that over to moles of the Freon 12. So from the periodic table, we know that 1 mole of CCl4 is going to be equal to 153.8 grams. From the balanced chemical reaction, for every 3 moles of CCl4 that are consumed, 3 moles of the CCl2F2 are produced. This is going to produce a total of 0.748 moles of the Freon 12. Likewise, we need to do the same calculation for the 115 grams of the SbF3. We know from the periodic table that 1 mole of SbF3 is going to equal 178.8 grams. From the balanced chemical equation, for every 2 moles of SbF3 that are consumed, 3 moles of CCl2F2 are produced. This is going to give us 0.965 moles of CCl2F2, or Freon 12. So from these values, this first one that we calculate is the smallest number of moles. So therefore, the CCl4 is the limiting reactant. Since we know that that's the limiting reactant, we're going to use that 0.748 moles to calculate the mass of the Freon 12 that's going to be produced. So we just need to do one more step, which is 0.748 moles of CCl2F2. Using the periodic table, 1 mole of the Freon 12 is going to be equal to 121 grams. And that's going to give us a value of 90.5 grams of CCl2F2. So this value right here is our theoretical yield. So that is part B for our problem. Part C is to calculate the percent yield. And remember, the percent yield is going to be the actual yield divided by the theoretical times 100%. And for this particular problem, the actual yield we determined in the lab was 80.0 grams divided by 90.5 grams, which is the theoretical yield, times 100% is going to equal 88.4%. And this is our percent yield. So that answers part C of this particular question. So to sum everything up, we were given a balanced chemical equation, and we said that 115 grams of each reactant were able to react. We were able to recover 80 grams of the Freon 12. From this, we can calculate the limiting reactant. So we convert over to the moles of the product for each of these reactants. Then, once we figure out which one the limiting reactant is, we take the number of moles produced from the limiting reactant, convert that over to grams, and that gives us our theoretical yield in grams of the product of interest, which in this case is our Freon 12. Lastly, we can calculate the percent yield because in the problem we were given the actual yield that was recovered in the laboratory, divided by the theoretical or the calculated value in grams times 100%, and that gives us a percent yield of 88.4%. The last problem we're going to perform from this section of the text kind of combines a bunch of things and even kind of taps back into what we talked about with Chapter 2 with nomenclature. So the problem reads as follows. Sodium and phosphorus react to form sodium phosphide. If 5.00 grams of sodium reacts with 4.00 grams of phosphorus, which in this case is P4, and the reaction goes to completion, what mass of which reactant is in excess? So first of all, we have to figure out what the limiting reactant is and what the excess reactant is. And in order to do that, we must first balance the chemical equation. So here we have sodium, and we're going to react that with phosphorus, which phosphorus exists in multiple forms. It's given in the problem here that it's P4, and this is going to give us sodium phosphide. Now, remember that sodium has a +1 charge, and phosphorus, when it forms an anion, has a -3 charge, so our formula is going to be Na3P. So now we have to balance this particular equation. On the left-hand side, we have 4 phosphorus. On the right, we only have 1, so we need a 4 in front of the product. That means we have 12 sodiums on the right, so we're going to need 12 sodiums over here on the left. So our balanced chemical equation is going to be 12Na plus P4 to give us 4 Na3P. We're given the amount of each of the reactants that we have, so now we need to determine the limiting reactant. So we'll first start with 5.00 grams of sodium. We know from the periodic table that there are 23.0 grams of sodium in 1 mole of sodium. In the balanced chemical reaction, there are 12 moles of sodium for every 4 moles of Na3P. This is going to give us 0.0725 moles of Na3P, which is our product. Now we'll do the same calculation, but instead we'll start with 4.00 grams of the P4. From the periodic table, we know that 1 mole of P4 is going to be 123.9 grams. From the balanced chemical reaction, for every 1 mole of P4 that's consumed, 4 moles of Na3P are produced. When we do the calculation, we get 0.129 moles of Na3P. This tells us that the 0.0725 is the smallest number, so therefore the sodium is the limiting reactant. So this means that this is also going to tell us that P4 is the excess reactant. So we need to figure out how much P4 is going to react completely with 5.0 grams of the sodium. In this case, we know that 0.0725 moles of the sodium phosphide is produced. So we'll take that number, the 0.0725, which is going to be moles of Na3P, and we need to determine how much P4 it's going to take to produce that. So for every 4 moles of Na3P, we have 1 mole of P4, and that comes from the balanced chemical equation. 1 mole of P4, if we look on the periodic table, is 123.9 grams, which gives us 2.25 grams of P4. And again, we want to express this in a sentence. What is this 2.25 grams of P4, and what does it mean? We can say that if 5.0 grams of sodium is fully consumed, it will take 2.25 grams of P4 to complete the reaction. So this is the amount of P4 that is consumed in the reaction when all of the sodium reacts. So we're going to take our initial value, the 4.00 grams of the P4. We're going to subtract from that 2.25 grams of P4. That gives us 1.75 grams of P4. Okay, so this is our initial amount of P4. This is the amount that's consumed during our reaction, and this is the amount of excess remaining after the P4 reacts with 5.00 grams of sodium. So this value right here is the mass of the reactant that is left over after our reaction completes, and the excess reactant here is our phosphorus. So this is a long, lengthy example, but come exam time, I would expect you to be able to complete this without any type of a problem. So be sure you go over your notes, you know your stoichiometry, and don't forget the stuff from previous chapters because it's going to creep up, and as we go through this course, we are going to keep building and building and building upon the foundation that we established in these first 3 chapters.